Okay, guys, Olivia is going to teach the 3502 wastewater workshop. Everyone give her a round of applause.
Okay, so I made some slides. Yes, slides. Okay. I put all of my my full course notes and a copy of the slides on this Google folder. So I'll do another QR code at the end, but just in case, because there's really not enough time to go through like the whole thing. Oh, did you need that? Oh, sorry. My course notes are like 52 pages though, so like not exactly the most summarized in the history of the world, but anyway. Let me know if it doesn't work.
No, it does.
It does? Okay, nice. Nice. Okay, so we're going to start off with water engineering. So this is Stefan's part. I think Sissy said some person called Steve was taking Stuart's section for wastewater. Stephen? Yeah. Have you been told whether it's like open book or closed book?
I think it's closed.
Closed. Yeah. Last year was closed on Inspira, so it's kind of annoying, but anyway. Okay, so these are our topics that I'm covering in this section of the crash course, but not covered are smooth channel transitions, gradually varying flow, and pipe networks. We just like didn't really have enough time, considering we're doing both halves of the course. But we're going to start off with open channel flow. So this was kind of a diagram that we adapted from something that you might remember in fluid mechanics. So on the left-hand side, you see how we've got our z's, we've got our y, and we've got our v squared over 2g. Does anyone remember what Bernoulli looked like from fluids? Yes?
Z plus P over rho
G.
gamma plus V squared over
2g. Nice. Okay. So we're taking Bernoulli and then we're going to adapt it for open channels. And we're also going to introduce this new thing where we have like these three different lines. So the bottom line is the channel bottom. So if we have a sloping channel, we have to take that into account. And then we also have this thing called water surface. So that's indicated by our SWS down here, water surface slope. And then we have our energy grade line, which you should be familiar with from fluids. Okay, so after that quick little recap, one other thing to note is under uniform conditions, bed slope, energy gradient, and water surface slope are constant and equal. So if you just keep that general diagram in mind when you're doing your questions, you should be right. So I'm sure you guys remember Reynolds number from 2500, right? Yeah. So remembering how we did Reynolds number in pipe flow, we had R equals VD over VU. And then we have like some values here for what counts as laminar and what counts as turbulent. In free surface flow, which is also like what we find in open channels, these numbers might slightly change, particularly down here for turbulent flow. So that's just something good to keep a note of. And when you have to classify things as turbulent or laminar, you'll have to be using these free surface flow numbers in your open channel questions. And then I've also got our constants here, which we should be familiar with from last year. All right. So the first equation they start you off with is something called the Chassis equation. And it can only be used in turbulent conditions. So it's kind of like an approximation, and it's a useful way to calculate velocity in an open channel. Your Chassis equation usually gives you flow values of 30 to 60 meters cubed per second. So that's kind of something that you can use to sanity check your answers. And as velocity in the channel increases, so does this thing called the Chassis coefficient. And the Chassis coefficient is the C down here, right? So we're told that we know that Q equals flow, so that's in units of meters cubed per second, and that's equal to area times velocity, which you should be familiar with from fluids. And then they take this approximation for velocity here using the Shazia coefficient, and then times it by the square root of the hydraulic radius times by S, which is the slope. Okay, so sorry for that quick rundown. We're also going to jump into how to find this C, so the Shazia coefficient. And this is just an example of like what an open channel flow might look like. We've got all of these different equations here for calculating the Shazia coefficient, and they look a little intimidating, but it's okay, we'll go through them. So up the top here, I've got this equation for the Shazia coefficient, 18 times log 10 over 12 times the hydraulic radius over Ks plus 2 over 7 times the thickness of the viscous sublayer. So they've kind of got a bit of a breakdown of what all of those premier rules mean. But the thing you need to remember is down here we've got two different cases. So these can help you kind of jump in and find your Shazia coefficient a little bit faster. If you think or if you're given in the question that your flow is going to be hydraulically smooth and turbulent, you can check that case by using this inequality here. So Ks is a lot less than 2 over 7 times the thickness of the viscous sublayer. In this case, that equation simplifies a little bit down to what we see on the right. And then if you've got rough turbulent flow, it simplifies again. So you can kind of make an assumption one way or the other, but you just have to make sure that you go back and check it at the end of your question. All right, moving on. We're going to look at a different equation now. So we've got something called Manning's equation. So sometimes you'll be given an n value, which is the Manning coefficient. So similar to how we had the C value for Shazia coefficient, we have another empirical equation, which means it was found via lots and lots of experiments. And they've come up with this list of n values. So we've got all these n values in this table on the side. You don't have to remember them. They'll probably give you one, or they might ask you to find it, like to go backwards and find it. And the Manning equation down here is velocity equals the hydraulic radius to the power of 2 over 3 times the slope to the half, and then all over n, which is that Manning coefficient that we talked about before. And they kind of change based upon the material that your open channel is constructed from. Okay. Now we're going to move on to another section. So this one's called finding optimal cross sections. And to find an optimal cross section, you have to find the minimum area for a specified flow, which remember to be Q. Or we have to design a channel with specific A, so specific area, for a maximum flow. And that can be really important when we know that we have to design certain channels for flood conditions, and we want to be specifying that maximum flow based upon what we think the flood conditions in that area might be. Okay, and I've got this like cheat sheet over here, which is a summary of hydraulic radius calculations for different channel cross sections. So this one is really useful when you see a question and they tell you it's a trapezoidal open channel. You can go straight to here and find the hydraulic radius, and rather than having to calculate it all by yourself, remembering that they've got that equation up here, RH equals A over P, so area over perimeter, and that's just the wetted perimeter in the channel. Okay. I've also got just a note here on some limiting values for hydraulic radius calculations for specific types of cross sections. So sometimes in your question you might be asked to find the optimal cross section of a channel that's very narrow and very deep. In that case, remembering that our width of our channel is B and the depth of water in that channel is Y. So our B over Y value kind of approaches 0. So our B is a lot bigger, like very tiny, and then our depth is a lot bigger. And then when we have that asymptote here, we can simplify down our hydraulic radius, and then that simplifies down, once you do the math, to b over 2. And if you just remember these two conditions, you can kind of just put them down in your working rather than having to substitute in 0 or infinity, which can be a bit annoying. And then in the other case, so b over y goes to infinity, this is probably the more common one. We're having a very wide and shallow channel, and so once you sub that all in, your hydraulic radius approaches y, which is the depth of flow in the channel. So that kind of just simplifies down those calculations, especially when you're finding optimal cross-section. Okay, and then we've got a bit of a summary of open channel equations and when to use them. So up here we've got our Chazzy coefficient equations. They've given you when to use them, so rough, smooth, or transitional. They've got that more complicated version of the Chazzy coefficient equation that simplifies down when we specify smooth or rough. And then sometimes they'll give you a constant, like in your question, but most of the time they'll ask you to find it. And then sometimes they also give you your Manning's values, that's your n. And then down here, this one should be looking kind of familiar to you. This one is Colebrook-White. Not sure if you guys remember that one from 2500. Yeah, and then down here we've got one for the frictional coefficient for laminar flow. So that one should also be familiar from 2500. All right, now I'm moving into something slightly different. So I'm not sure if you guys remember from 2500 this thing that they briefly talked about called Froude number. No? That's okay. It's kind of similar to Reynolds number. It's just like another measure of like a specific type of flow. So over here on the right, I've got some descriptions of what these flow conditions might look like in practice. We've got something called the Froude number, which we use to describe these flow conditions. So FR equals U over the square root of G times Y. So remembering U is the same as velocity. And then we still have that same Y, which is the depth of water in the channel. And then we've got these three conditions based upon what value our Froude number takes. So flow is subcritical if the Froude number is less than 1. Flow is supercritical if the Froude number is greater than 1, and flow is critical if it's equal to 1. So what are the significance of supercritical, subcritical, all that? Over here on the right, we've got this example of supercritical flow. So we notice down here, we've got a really shallow and fast flow. And then over on the right, we've got subcritical flow, which is really deep and quite slow moving by comparison. And in the middle, we've got all of this turbulence. We've got all this water aeration. We've got this thing called a hydraulic jump. And this is where our flow is critical, and it shifts from supercritical to subcritical. And if you have to remember one thing from this course, it should probably be that you can't go from supercritical to subcritical without one of those hydraulic jumps. So let's talk a little bit about something called specific energy, because that will also help us out in this situation. For a general channel cross-section, we use something called specific energy, denoted by E, and the unit is in meters. And the equation here is E equals Y plus V squared over 2G. We've got some simplifications here for a rectangular channel. So we know our flow per meter width is Q over B, which is the width of the channel. And that simplifies down to V times Y for a rectangular channel. And then we get this equation down here for specific energy. And just some things down here on the right, specific energy may increase or decrease based on elevation. It's kind of a similar measurement to head, which is something that you should be familiar with from 2500. And as your elevation increases, which is your Z value, then your specific energy decreases. So they've got this inverse relationship here. All right, and then we're going to do something that helps us visualize this relationship a little bit more. We plot this relationship on a graph of E versus Y, so specific energy versus depth. we've got specific energy on the x-axis and depth on the y-axis, and then we notice that it's kind of got this like asymptote here where y equals e, and another asymptote here where y equals 0. And we know that's the case because this is a cubic function. Alright, and because of these asymptotes, we're left here with like a little minimum value where we've got minimum E at this specific depth of water in our channel. So this minimum E is often called E critical, so critical specific energy, and then critical flow depth. Alright, so for any given value of E, there are up to 2 possible depths of water in our channel called alternate depths. And we know that because we've got this down here where we see these 2 possible E values for our, we've got two possible Y's for our 1 specific E value. Okay, I know it can seem a little abstract when you're just looking at a graph, but we kind of split this graph up. So above this E critical point, we've got subcritical flow, remembering that's our really deep and slow moving flow. And then supercritical is a really skinny one that's moving really fast. And for rectangular channels, I've just got this point down here when fluid number equals 1 or y equals the critical flow depth. Obviously, flow is critical. When fluid number is less than 1 or when y is greater than the critical flow depth, flow is subcritical. And remember that because subcritical flow is going to be thicker. And then the opposite is true for our supercritical. Okay, continuing on with our concept of critical flow. For general cross sections, we have to take this dA equals b times dy equation, and when q is constant, critical flow velocity is critical flow equals the square root of g times d. Okay, and they've given you what d means down there. So we're going to talk a little bit more about this whole idea of hydraulic jumps. That's what's going on in the center of this image down here. So some characteristics of hydraulic jumps include rapid deceleration of flow, lots of turbulence and air entrainment, and that just means air getting swept up in the water, lots of bubbles and things like that. Then we've got spray and sound, energy losses, and hydraulic jumps are used to prevent bed scarring, particularly on the spillway of dams and things like that. And they're also used to mix liquids and aerate water and wastewater, which you'll probably see pop up in the design of things for wastewater treatment plants. Okay. Yeah. Bed scarring is when you have like a concrete spillway, and then because of the force of the water, it starts to tear away at the concrete. So it can be really damaging for like the long-term like safety of a dam, and so they really want to avoid making sure they like taking away that concrete, because then they have to rebuild it. Yeah. Alright. So moving into where we calculate our hydraulic jumps to occur. So this is just our diagram on the right. We've got over here our skinny, like shallow, fast-moving flow. Does anyone want to tell me whether that's subcritical or supercritical? Yeah. And then on the right? Subcritical. Yeah, subcritical. Nice. So here in the middle we have our hydraulic jump, and Y1 and Y2, which are over here, are these things called conjugate depths. So you'll either be told the upstream conditions, which is location 1 down here on the left, and have to find the Y2, or vice versa. You have to make sure that you pick the right equation out of these two. That will help you find the missing piece of information that you need. And this kind of simplifies down once again for rectangular cross sections. Things get a bit easier, so just keep that simplification down in mind. All right. Then I have a quick recap of pumps, some things that you should be familiar with. Pumps transfer energy from the rotor to the fluid, and they add energy, also known as head, or transfer fluid from one location to another. So we've got our equation down here for pumps. should be familiar to you once again. Then we've got our power output, so P out equals rho times G times flow times the head of the pump. And that's measured in watts or joules per second. Okay, and then efficiency is the power out of the pump over the power that you put in. Okay. Now I've got like a bit of a comparison table between two types of pumps they introduced to you in 3502. So there's one called a rotodynamic pump, and then the other is called positive displacement. What happens inside for a rotodynamic is continuous free passage of fluid between the inlet and the outlet. You often use it for low pressure and low head applications, viscous fluids, but the con is that it's not self-priming. So it takes a little bit more effort and maintenance to start up. And then examples of that type of pump are centrifugal, radial, mixed, and axial. And then by comparison, we have positive displacement pumps, so they move the exact same volume every single time from inlet to the outlet. So they're often used in like medical applications, high head and low flow applications, or fluids that have a large range in viscosity. Also use them for slurries, but they need regular cleaning and lubrication, and examples include Archimedean screws. All right. Yeah.
Did you say can't use them or not suitable for? Because on the slide you said can't.
Where?
So it's not suitable for viscous fluids and slurries. Because you
Is
said
this-
you can also use it for slurries.
Oh yeah, sorry. Not suitable. Not suitable. Sorry. Oops. Okay. Now we're gonna switch over to wastewater. I've got another little breakdown of what we're covering here. So we've got classifying solids, water hardness, screening and rag removal, sedimentation, coagulation, flocculation, the definitions of BOD, NOD, and COD, and then anaerobic treatment and methane production. But I've also got quite a lot of things we're not covering in this one, so make sure you go over to my full course notes if you're looking for more information about that. Okay, so starting off with classifying solids, this diagram here, this tree diagram, is something that I think like one of the biggest questions in wastewater was on last year. It's quite a simple concept once you've got it, but make sure that you have this tree diagram memorized, because Stuart definitely tested us on it last year. So we split total solids down into suspended and dissolved, and then we can split each of those into something called volatile versus fixed. What I mean by volatile is that if you heat it up, it will volatilize. So that probably is not a super helpful definition. Basically, you won't be able to measure it when you weigh your substance afterwards. So what they do to figure out the amount of volatile versus fixed, they do something called heating up in an oven or heating up with a certain type of like paper. They measure it before and after, and then the difference is the volatile. So I'm gonna go into these definitions in a little bit. One more thing to note down here, total solids is measured in milligrams per liter most of the time. And they'll probably put in the question something like the mass of the container was X, the mass of residue was Y, and then make you figure it out from there. So going into these definitions in a little bit more depth, total suspended solids, also called TSS, is solids collected on a filter paper per volume of water filtered. So that's the stuff that doesn't get dissolved into the solution and gets caught on top of that filter paper, and that's equal to total dissolved solids plus total suspended is equal to total solids. So that's like this component at the top. Then we've got volatile, so fraction of solids which can be volatilized or combusted under standard conditions, and those standard conditions are 550 degrees Celsius in a furnace. Fixed solids are the ones that don't get volatilized, and then total volatile suspended solids are the solids collected on filter paper which can be combusted later on. Something to note down here is in the question they might refer to ashless paper or this thing called glass fiber filter paper. Ashless paper means that it combusts with no ash or carbon left behind, which is contributing to that weight. So you don't need to like do any sort of extra maths with that one. But for glass fiber filter paper, you have to subtract the dry weight of that paper to make sure that you include it in your calculation. And then total fixed suspended solids is TSS minus TVSS. Okay. Now we're going to talk about this thing called water hardness. It's caused by excess calcium and magnesium in the water. Sometimes you guys might see, I don't know if it's necessarily in Sydney water, but maybe if you go over to Perth or something, you can see this extra like scour on your like water fixtures and things like that. It's not an actual like issue. It's just like the collection of extra calcium and magnesium on water fixtures, but it does cause some quality issues. So soaps might not lather as well, and it produces this scale, which we see over here, and then it can affect like the long-term lifespan of water heaters and toilets. So you kind of want to avoid like really hard water, but you also want to avoid really soft water. All right, so you can remove some of this calcium and magnesium by various processes. These can include chemical precipitation, ion exchange, and membranes. And sometimes in your questions you'll be asked to calculate total hardness of the water. That's just the number of moles of Ca2+ ions and the number of moles of your magnesium 2+ ions. Often reported as CaCO3 milligrams per litre. And then we've got some classifications over here on the side. Pretty sure they usually like refer to them. Yeah? Yeah, it's because CO3, so this is that thing called a carbonate ion. Well, let me use the board actually. If you guys didn't do chemistry in high school, this is something called a carbonate ion. And so it's calcium, carbon, and 3 oxygen atoms, and then they pull together to produce an overall charge of 2-. And then we also have our calcium, and then we have our magnesium, which they call Mg, and that's 2+. So for water hardness, they kind of get attracted to each other because this one is 2+, this one is 2-. They can combine to produce calcium carbonate, so that's CaCO3, or they combine with magnesium, so that's MgCO3, and then they form this calcium carbonate or magnesium carbonate, and that's kind of what they use to measure it, because oftentimes like if it's in like dissolved in the water, it'll be in ionic form, so with these charges, but they just prefer to use it as this for like notation purposes. Okay, moving on. Oh yeah.
How come they only report calcium and not the magnesium carbonate?
Yeah, it's just like, well, they never really gave us an explanation for that when we were learning it. I think it's just like a notation thing or like a standard procedure type of thing. But maybe it also depends on like the specific water conditions of the area, because some areas will probably have more magnesium, and that's like what's contributing to their water hardness more than calcium. So I don't know. Maybe it's a Sydney thing. I'm not really sure. Sorry.
Okay. Oh, and one more thing.
Yeah.
You said water softness is also bad. Why is too soft of water bad?
I don't really know. I guess they probably kind of want to aim for like this moderately hard range, but yeah, they haven't really explained that to us because usually Sydney suffers with like overly hard water. That's not something that they put in the lecture notes, sorry. I can research it for you afterwards if you like.
No, it's not good.
Okay. Alright. So we're going to talk a little bit about wastewater treatment processes. You start off with this thing called screening, grit removal, then move into a primary clarifier, aeration, secondary clarifier, chlorination, and then you take out the biosolids and then you remove this effluent water and put it into streams and rivers. Sometimes out at Wollongong and Shell Harbour wastewater treatment plants, they have these massive pumps that they discharge them straight out to the ocean. I know they also do that at Cronulla and Malabar, but yeah, we have 4 main big wastewater treatment plants servicing all of Sydney. So these wastewater treatment processes have a lot of weight on them. Alright, so starting off with screening, that's at the very start of this process. It's the removal of solids by passing the water through these things called apertures, which are the openings in this screen down here. And these are smaller than these solid particles. So bar racks and screens are usually installed at an incline in order to help with that debris removal. And then they have to mechanically clean them every now and then to make sure they scrape off all this extra stuff, because people throw rubbish down their toilet that obviously you can't treat in some of the later stages because it'll break the equipment later on. So some equations to remember for screening. We've got flow equals volume over time, and then volumetric flow rate is also equal to area times the flow velocity. Okay, it's typically used for removing solids that would block downstream processes. I don't know why I've forgotten processes there. Anyway, removing stuff that would damage the pumps, protecting potable waterwork intakes, and removing algae. Some other screening calculations, sometimes they like you to calculate the head loss through the bars of the screen. So that's this HL value. We've got this C here. That's not the Chazzy coefficient. This is something else called a discharge coefficient. It's 0.6 for clogged screens and 0.7 for clean screens. And these values are going to be ones they'll ask you to memorize for the exam. And then it's velocity of flow through the bar screen squared minus velocity of approach in the upstream channel squared over 2G. Okay, moving on to rag removal and disposal. They have this process called comminution, which is mechanically breaking up these solid materials. Then they have grit chambers to remove sand, gravel, and minerals, and then constant velocity channels. So they run the water through these channels and then wait for the solids to kind of fall to the bottom, and then they scrape them off the bottom. Alright, these constant velocity channels can be parabolic or trapezoidal, and then they ask you to find the settling velocity for solids in that water. So that's the equation here. Make sure that you're referencing turbulent, not laminar flow conditions. Alright. Now we're going to talk about sedimentation tanks. So that's the settlement of particles which have a higher density than the liquid in which they're suspended under the influence of gravity. We have 2 types of settling tanks. First one is horizontal. That's the one we've got over here. Simple rectangular tanks that are around 2 meters deep, and sometimes they like to make you calculate the length over width ratio of tanks. Usually it's in the range of 2 to 5. And then the water enters one end, leaves via an overflow weir as solids settle to the bottom. So this is that overflow weir right here. And then down the bottom, all this sludge you see is mechanically scraped, usually by a chain. Okay. The other type is vertical and radial, but I don't have an image for it. They usually take up less space, so it's good for wastewater treatment plants in areas where land is expensive, so i.e. Sydney. Raw water enters via a diffuser drum in the centre, and then that directs the flow downwards towards the bottom of the tank. And then liquid flows upwards for a vertical flow tank, or outwards for radial flow. Okay. Then in calculating settling and sedimentation, usually our settling and sedimentation tanks, the flow conditions are really, really slow, because if it's too fast, those solids in that water will just be swept up and won't be able to fall to the bottom. So using laminar flow conditions, we have these two equations here. You can use either one depending on what information you're given in the question. I've also got our pronumerals down here, just so you have them on hand for reference, and make sure that you're keeping a note of the units as well. Okay. I've got a couple more equations here for particle settling time and basin flow rate. Sometimes they'll ask you to calculate time required to settle a specific particle. So that's time equals h over vs. Down here we've got h, which is the height of the tank. And then the same particle will travel a distance L in the same time. So that's time equals L over the velocity. And then critical settling velocity is written down here. Then we kind of put all of those things together to find the flow rate through the tank, basin flow rate. That's Q equals VH times H times W. And then down here we have something called the hydraulic retention time, or HRT. So that's tau equals volume over Q. And remembering we have that Q calculation up here, so you can just sub that one in. Yeah?
Is all of this related to laminar flow? Talk about this settling.
Yeah.
So this is all laminar.
Yeah, all laminar. Yeah. They kind of have to slow down the flow of the water for that sedimentation process to occur. But sometimes they'll completely stop the flow if the bar screens get like too clogged up, and they have to go in and manually remove all of that stuff. Okay, next we're going to talk about something you guys are going to do in your lab. So this is called coagulation. Yeah, Patrick, you've seen this from the lab last year. So you start off with a really murky sample of wastewater, right? It looks pretty horrible. I mean, it looks kind of horrible throughout, let's be real. And then they add this thing called a coagulant, and it collects all of those solids into these things called colloids, and then they fall to the bottom, and then you're left with a lot cleaner solution on top. And this stuff down the bottom is called the substrate. So after all of your rag removal and sedimentation processes, your particle size is now between 1 nanometer and 1 micrometer in diameter, just to give you guys a bit of perspective. The particles in it can include microorganisms, trace organic chemicals, algae, inorganics called colloid particles, and these colloidal particles often have an overall negative charge. So we see that in this diagram up here. Our colloids all have these negative charge, and then the surrounding solution is positive. So the insides, the colloids themselves, will be attracted to this positive charge on the outside here, and then the positive charges will be repelled, because you can kind of imagine them like magnets, but then the same will happen on this side to this colloid. A cationic chemical, a good way to remember what a cation is if you think of a cat, you think, oh, cute, fluffy, happy, positive, they give you positive vibes. A cation is positively charged. An anion kind of sounds like an onion. Onions make you cry, negative vibes. An anion is a negatively charged ion. So a coagulant usually has a positive charge, so that's this positive stuff around here, around the colloids, and it's added to attract the colloidal solids and neutralize their surface charge. Some examples of coagulants they might use around Sydney include aluminium sulfate, which is often called alum, or different types of chlorides. Then we go into something called flocculation. So we have like slow mixing of that solution that you saw on the previous slide. It allows these smaller colloidal particles to grow and then coagulate into larger particles called flocks. And if there's too much agitation, so if we stir too fast, there will be not enough collisions for the flock to grow. But if there's too little stirring, there'll be not enough for it to grow. If there's too much, then the flocks kind of break up and then you can't collect them very easily. Then they do this thing that you do in your lab called jar testing, and they use that to figure out the dosing of the coagulant. And you'll see this in person in like week 7 or 8, I think. Yeah. Okay. Now describing some biological processes in wastewater, we have this measure called BOD. That's called biochemical oxygen demand. They often represent this thing called organic carbon as C6H12O6. Basically what you need to remember is that bacteria need carbon to grow and reproduce, and some consume organic carbon, which is this stuff right here, and release CO2 when doing so. That's kind of what we do, this thing called cellular respiration. Whenever you breathe, you're doing that right now. So our organic carbon reacts with our oxygen to produce CO2 and water, and our biological or biochemical oxygen demand is a measure of how much oxygen is used up. So it's a good way to tell how many microorganisms might be completing this process in your wastewater and how much you still have left to treat. You can kind of think about it in a way that is like, you wouldn't want to drink water that has a really high BOD value because you know there's lots of microorganisms in it. Next, we've got this thing called NOD, nitrogenous oxygen demand. It's usually a 2-step process involving bacteria that use inorganic carbon. So there's that carbonate ion and this bicarbonate ion, HCO3-, as their carbon source. You guys don't really have to remember all of these equations. You do have to remember the one on the previous slide though. It's a good way to measure like how much ammonium, which is this ion here, NH4+, and nitrate, NO2-, is in your wastewater. Because if we discharge wastewater that has a really high ammonium and nitrate amount, it can be really, really bad for the environment. And they cause things like eutrophication, algal blooms, a lot of like water quality issues. All right, moving on, we have chemical oxygen demand. This is something that we figure out in the lab using this thing called titration. You don't really have to know how to figure out how to do a titration, but the definition here was in last year's exam. So just make sure that you remember the definition. You can kind of ignore this equation down here. But the definition is the amount of oxygen consumed in the chemical oxidation of organic matter. So that's these ammonia and nitrates that we talked about on the previous slide. And they usually do that by adding this strong oxidant called potassium dichromate. They might do it with other types of strong oxidants, but this is like the main one they use. Okay, now we're going to talk a little bit about anaerobic biological treatment processes. So anaerobic just means no air. So instead of all these other processes that we've talked about that have been open to the air, usually placed in like big fields and things like that, these happen instead in tanks. So pros are no aeration required, so you don't have to stir it, which means less energy. And then it also produces less sludge. It's a more stabilized product by the end of it, meaning that there's less chemical reactions and activity from microorganisms by the end. Then there's also low operating costs. It can treat variable loads. So if you have a lot of like people in a specific area that come in for like a big event, and then obviously you end up with lots of wastewater, then you're going to have that variable load issue. Sometimes your wastewater treatment plant won't be able to cope, but if you have these anaerobic digesters, they can kind of help to deal with that. And they also produce methane as an end product. Why might methane be a pro? Does anyone know what we can use it for? Actually, I feel like you should know. You should know. As an environmental engineer. You'll know. Think about energy.
Use it as like in fire.
Kind of, yeah. You can burn the methane for power. Yeah. So usually methane's a bad thing, right? You know how they always complain about too many cows fighting too much, and then there's too much methane contributes to global warming. instead, because we already have this methane, we can burn it off and use it to recover energy. So that's why a lot of wastewater treatment plants now have, rather than flares, where they just burn off that methane and produce no like energy generation from it, they also have generators on site. By contrast, we have a couple of cons. So it's a slow startup and a long retention time, so they have to keep that wastewater in the tank digesting for a long time. It can also be sensitive to toxic compounds, so sometimes you'll find things like heavy metals in your wastewater, especially if you're coming from like an industrial area. Maybe if there's lots of textile processes going on, you might end up with heavy metals there. And also there's high capital costs, produces odorous and corrosive compounds, so maybe not so popular in really populated areas. You might get complaints from the neighbours. And it also requires post-treatment, so once it comes out of that, that digester, to remove BOD. So they've still got microorganisms in there, and you have to treat them with heat. So let's talk about how it works. These equations were also in last year's exam, so unfortunately you do have to remember them. First off, we have this process called hydrolysis. So complex biochemicals such as proteins, lipids, carbohydrates, and nucleic acids are broken down into long and short chain fatty acids. It's carried out by enzymes, which are excreted by the bacteria that's in that wastewater. After that, we have this thing called acetogenesis. It converts molecules such as this organic carbon and water into something like this, which is an acetic acid. You might also know acetic acid as vinegar. It's like a very common short chain acid. Then we've also got production of hydrogen and carbon dioxide. After that, we have methanogenesis. So we convert acetate to methane, and that can happen in two different ways. We've got this first one down here where methane can be produced directly from acetate. So we've got this acetic acid down here, which splits off into methane and carbon dioxide. And then otherwise you can produce gas from H2 and CO2. So that's these products up here that we already have there from the acetogenesis. That CO2 plus hydrogen goes to methane and water. All right. Now we're just going to finish off with biochemical methane production. So this is kind of what I was hinting at before with that energy production. So it can be a really good way to produce extra energy from stuff that would otherwise just be burnt off and probably be worse for the environment. So it's a test determining methane potential and the biodegradability of wastewater and waste biomass. And we want to know this methane potential because we want to know how much energy we can generate. The substrate, which is like that sludge at the bottom, is mixed with anaerobic bacteria culture from an active digester. The bottles are usually mixed for 30 to 60 days at a constant temperature, and then methane and carbon dioxide are produced due to the anaerobic degradation of organic matter. So that was those chemical equations that we went through on the previous slide. Then they measure how much methane is generated. So we've got a couple of equations down here that they usually use for calculating the amount of methane that gets produced. We want to see our chemical oxygen demand that's going in, so that's our influent, and that's equal to the stuff that's coming out, so that's the effluent, plus the stuff that's in the gas, plus the stuff that's in the sludge. Then we figure out the amount of methane produced in our volumetric flow rate, and that's equal to 0.35 times our methane over our kilograms of COD, times our influent cod, so that's the cod I here, minus our effluent cod, the cod E, and just making sure that unit is in the right form, times by our flow rate. Okay. One more thing. I'm pretty sure this is our last equation. This is an example of a flare. So when they have too much methane, they'll have to burn it off. It looks pretty cool when you get to go there at night. So our P is our methane production, and that's equal to our mass of substrate fed into the anaerobic digester times by the total solids content of the substrate, and that has to be in the form of a mass fraction. So that's just like the amount of mass of the solids over the total mass going in. Mass fractions also have no units, so they're dimensionless. Times that by the volatile solids content of the total solids, remembering that we had that tree diagram that split off our volatiles from our fixed, and then we times that by what we found the biochemical methane potential to be, and that was on the previous slide. Okay, that's what we have time for. Well, we finished quite early, but anyway, this is the same QR code with my notes, and thanks for listening, guys.